We have already said that electrolysis is a decomposition of a substance by an electric current. So we could say that is a process by which an electric current is passed through a substance and it is decomposed by the same. Now for a substance, an ionic substance for that matter, to conduct an electric current, it must not be in solid state, because in the solid state the ions are just vibrating, they are not moving. It doesn't have mobile ions. So for us to have mobile ions, therefore, there are two things we can do. We can melt the substance. When you melt the substance, we will get what we call a binary electrolyte that consists of only two ions. The other thing that we can do with the electrolyte is to dissolve it in water. So still, the ions will be free to move in the solution. So it will be able to conduct because the ions are mobile. But then something happens when you dissolve a substance in water. So apart from the ions from the substance you are dissolving, you will get ions from water, because water is capable of ionizing to form the hydrogen ions and the hydroxide ions. You may tell me that these ions are very few, and it is true, because at 25 degrees Celsius, I'm only expecting some 10 raised to power minus 7 moles per liter, 0.000001. So few those ions may be. What you realize is, if you remove the hydrogen ions, you will favor the process that treats the formation of the hydrogen ions. So they may initially be few, but they are inexhaustible, because we have a lot of water, so the process will continue to regenerate the ions that you remove. So water becomes a real participant in the electrolysis. So what am I saying therefore? If I dissolve anything in water, I will have the ions from the water interfering with the discharge. So if I dissolve copper sulfate, I will have the cations, copper ions, hydrogen ions. The anion, sulfate ions, the hydroxide ions, because I have both the ions from the solute and the solvent as well. So if you can think, if I dissolve sodium chloride in water, what ions will I have? Right? So I hope you've said sodium ions, hydrogen ions. Those are the cations. Then what about the anions? Chloride ions, the hydroxide. The moment you remember that, you are almost through with this particular concept. That concept will be home and dry. So don't forget that when you dissolve a substance in water, apart from the ions in the solute, you also have the ions from the solvent. And I want to repeat that so that it sinks. Because that is where we always go wrong. If you forget the ions from the water, you will answer that question wrongly. You will not be in a position to tackle the question correctly. So remember, the moment you dissolve a substance in water, you introduce other ions, the hydrogen ions and the hydroxide ions. So don't just concentrate on the sodium chloride that you are dissolving. Also, know that there are ions from water. Now, having said that, I want to say one other thing. That at any one time, you cannot have two ions being discharged. It is going to be one of them. So you may be having the sodium and the hydrogen ions, but you're not going to go get sodium and hydrogen both being discharged. They may move towards the cathode, but only one of them will be discharged. We talk of something called selective discharge or preferential discharge. Preferential from the word prefer, it is preferentially, it is preferred over the other, or it is selected over the other ion. But how do you decide on what is going to be discharged between sodium and hydrogen? Between the OH and the chloride, how do you decide on what is going to be discharged? Are you going to do some guesswork? And the answer is no. There are some factors that affect the preferential discharge of ions, and these are position in the electrochemical series, the concentration, and the nature of the electrode. So those are the three factors that will determine what will be discharged at each of the electrode. Now let's start with the very first one, position in the electrochemical series. The electrochemical series can be equated to the reactivity series. Now look at a scenario where sodium is forming a sodium ion plus an electron. Now sodium is ionizing to form the most stable form, that is true, and energy will be produced. The amount of energy that you get from that reaction will depend on how reactive a substance is. So if I am changing from hydrogen to form a hydrogen ion and an electron, I will still get energy. If I am changing from potassium to potassium ion plus an electron, I will get energy. In fact, I know that there will be so much energy that the hydrogen will ignite. There will be a lot of energy to melt the sodium, but not enough to ignite, because sodium is less reactive than potassium. So the more reactive a substance is, the more energy you are going to get when you react it. So I'm expecting, if I arrange these reactions in order of the amount of energy I get from that, I will start from that as the highest, I'll go to that, and that will be the third. Now, in this case, I want to move the reverse direction. Now from sodium plus an electron to form sodium. That is the direction I'm going. So if I got energy here, I must supply energy there. Energy must be supplied, because you cannot create nor destroy energy. If you got energy when you produce the sodium ion, you must supply energy when you get back to the sodium ion. And we have said that you will need more and you will get more energy there. So if you are taking from potassium to the potassium atom, you need more energy than this process. So if, for example, you got say 10 kilojoules there, then here you will have to get about say 5 kilojoules and maybe 1 kilojoule. Now you have to supply, for this you have to supply 5 kilojoules. For this you have to supply 10 kilojoules. For the hydrogen plus an electron to form hydrogen, you have to supply 1 kilojoule. So you have to supply less energy here because you have gotten less energy then. So at any one time we know that processes will refer to take the route that requires the least amount of energy. We have said that very many times, that if sodium has two options in reacting, it can 281, it can either gain 7 or lose 1. It prefers to lose 1. Then you went to the catalyst. So the catalyst lowers the activation energy. Therefore, the reaction takes that one that requires less energy. So the same will apply here. You need the reaction that requires less energy is going to be the preferred reaction. in this case, if you have sodium competing with hydrogen for discharge, you are either going to supply 1 kilojoule or supply 5 kilojoules. Which one do you think will happen? Of course, the one where you supply 1 kilojoule. So what are we saying therefore? When you have a situation, you look at the two substances that are being discharged, sodium and hydrogen. Which one is more reactive? Sodium. Therefore, you need to give more energy for you to get back to the sodium atom. So the one that is preferred is the hydrogen. So in a nutshell, therefore, I will say the less reactive substance is the one that is preferentially discharged. So, but now you don't have to memorize the whole of the reactivity series, because, for instance, when you get to the metals, you're always going to be comparing hydrogen with something else. Hydrogen is going to be compared with something else. So all you need to know is hydrogen is only more reactive than copper, silver, mercury, gold. So when hydrogen competes with anything else apart from copper, silver, mercury, and gold, hydrogen will be preferred. It will be preferentially discharged. But when hydrogen competes with copper, then copper gains preference. When hydrogen competes with zinc, hydrogen gains preference because hydrogen is less reactive. So the less reactive substance is the one that is going to gain preference. When you get to the non-metals, then the OH is lowest in the electrochemical series. The lowest is the least reactive or series. It's the one that is most readily discharged. So then when the OH competes with anything, name it, as long as it's negative, then the OH will gain preference. As long as the factor that you're considering is the position in the electrochemical series. Let us look at an example here. The electrolysis of dilute sulfuric acid using graphite electrode. Now, what are the ions present in dilute sulfuric acid? Now, the cations are, we are talking about sulfuric acid, so which should ionize to form hydrogen ions and the sulfate ions. Then it is aqueous, therefore H2O, now this is not reversible, H2O to form hydrogen ions and the hydroxide ion. So what are the ions present? The hydrogen ions, that is a cation, the sulfate ions and the hydroxide ions are the anions. Now which ions are going to be discharged? At the cathode we don't have much of a choice, it is just hydrogen. So H gains, because reduction takes place at the cathode to form hydrogen gas. So you'll observe some bubbles of a gas that burns in and pops out when impure. Now at the anode, we have the OH competing with the sulfate for discharge. What have we said? OH is lowest in the electrochemical series. So what is the reaction for the discharge of the OH? So the OH will lose an electron. Otherwise, that is at the anode, and oxidation is lost. So we'll get something that looks like that, and the electron. So we can subtract that. But this one does not exist. Two of them will combine to form what? A water molecule and an oxygen atom. This one does not exist. So we'll need two of that. So an oxygen will combine with another oxygen to form an oxygen molecule. So what do we have? We need two oxygens. We need two oxygen. So this reaction must be multiplied by, that reaction must be multiplied by 2. That reaction must be multiplied by 2. Now, in which case, therefore, okay, what did I say? Oh, fine, fine. I will need to combine two of these. I will need to combine two of that so that they can form a water molecule and an oxygen atom that does not exist. So that means I need 4 of that. I need to multiply the whole of that by 4. And you can add up the equations. I think at the end of the day, these 4 OH are going to cancel. 4 OH are going to cancel. The oxygen atoms are all going to cancel. They are on both sides of the equation. So what will I have? 4 OH negative in solution, forming 2 waters or 4 electrons are there. 2 water molecules plus an oxygen molecule plus then the 4 electrons. So liquid gas, and that is the equation of a reaction at the anode. That's the equation of a reaction at the anode. So it's going to be a very common equation. So it's better to learn how to write it. Just know how to write that equation. Alternatively, you could just start by just write OH will form water plus oxygen plus an electron. Then I balance it. I have three oxygen. I have that gives me 3 oxygens. I can put a 3 here, but these 2 hydrogens cannot be balanced now. So I need to make this one a whole number so that I can have 4 of the hydrogen. Now is that equation balanced? And this should be negative. If you don't put the negative there, the equation is not going to be balanced in terms of the charge. So that is aqueous 4 oxygen, 4 hydrogen, and then now that there are 4 of them, you'll have to lose 4 electrons in gaseous state, in liquid state. That is the equation of the reaction at the anode.
Electrolysis of water. This is an electrolytic cell used for the electrolysis of water. It is called the Hofmann's voltmeter. Observe the parts of the voltmeter. Acidulated water is the electrolyte taken in the limbs of the voltmeter. The electrodes, anode and cathode, are made of platinum. Anode is positive while the cathode is negative. Observe the circuit closely. Note that the anode is connected to the positive terminal of the battery and cathode to the negative terminal. On the passage of electric current, water dissociates into hydrogen ions and hydroxyl ions. At the cathode, the positively charged hydrogen ions are discharged as hydrogen atoms that form hydrogen molecules. At the anode, the negatively charged hydroxyl ions are discharged that form water and oxygen gas. Observe the amount of products, oxygen and hydrogen, collected in the limbs of the voltmeter. The amount of hydrogen collected is double the amount of oxygen. Listed here are the reactions that take place during the process of electrolysis.
So there's a sulfuric acid that forms hydrogen gas there, and then it forms the OH, the equation. This equation must be committed to memory. So you have bubbles on each of the electrodes. Now, you note that this process is, we are removing the ions that makes up water. So we are breaking down water to hydrogen and oxygen. The hydrogen, so it's the hydrogen ion that makes water, it's the OH ions that makes water. Water broke down to H and OH. And those are the ions that we are removing. So we call this process the electrolysis of water. Why do we call it the electrolysis of water? Because the ions being removed are the ions that makes up water. Now, the other thing I need to note about that is that because we are removing water, we are going to have more sulfuric acid per unit volume. You are removing some water. So you are leaving sulfuric acid in the solution. The concentration therefore increases because you are removing the solvent, you're not removing the solute. So the concentration will increase because you are removing water. You are removing water. Now allow me also to note this one thing, that for every 1 mole of oxygen, you need 4 moles of electrons. Refer to the equation. 4OH loses 4 electrons to form 1 mole of oxygen. But those 4 electrons, 2 electrons will be required per mole of hydrogen. 2 moles of electrons per mole of hydrogen. What does that mean therefore? The volume of hydrogen is going to be 2 times the volume of oxygen because you need more electrons for oxygen. Actually 2 times the moles of electrons are required per mole of oxygen than per mole of hydrogen. So when you look at the setup, you will discover that if you are correcting the 2 gases, the volume of hydrogen, volume of oxygen. The volume of oxygen is half the volume of hydrogen. In fact, you can use the formula of water to remember that you have twice. For every mole of water, you have 2 times the number of, you have 2 times the amount of hydrogen as the amount of oxygen. But they don't use this to explain it. Only use it to remember because it's a question of the amount of electricity that is required per mole of each of the gas or per volume of each of the gases. So per volume of hydrogen, you need half the amount of electricity as per volume of oxygen. Another example, we are doing the electrolysis of zinc nitrate. Maybe before you continue to look at the way I've tackled that particular electrolyte, why don't you take a moment and complete the table for the electrolyte at hand. What is the electrolyte that we are handling? And what electrode are we using? What are the ions present? Just record the cations and the anions. And which of the cation is discharged at the cathode and why? Write the equation. And what about the anode? What is discharged? And what is the reason? At the back of your mind, just get to know why is it that substance is being discharged. And what do you see at the cathode? And what do you see at the anode? Are there some other characteristics of the electrolyte that will be affected? Like, what will happen to the pH, the solution? What about the color and the concentration too? What will happen to each of those characteristics? Then you can also look at what I've come up with for the same electrolyte. What are the ions present? So zinc ions, nitrate ions, from what? Zinc nitrate. Then hydrogen ions and the hydroxide ions. These are from water. These ones are from zinc nitrate will give us those ions. So we have the zinc ions and the hydrogen ions from okay, then we have the hydroxide and the nitrate ions. So what the zinc is competing with hydrogen for discharge. What gains preference? Right? We said that the less reactive will gain preference. And hydrogen is only more reactive than copper, silver, mercury, and gold. So if zinc and hydrogen is less reactive. So hydrogen gains preference, you get hydrogen gas. Now at the anode OH is lowest, so it gains preference. What are the observations? We get bubbles and you also get bubbles. Note that again this is the electrolysis of water, and what happens to the concentration of this solution? Yeah, we are removing water. We are removing that which constitutes water, OH and H. So the concentration should increase. And again, for every mole of oxygen, you need 4 moles of electrons. But if you use still 4 moles of electrons here, you get 2 moles of hydrogen. So the volume of hydrogen is 2 times the volume of oxygen. Now, the other thing I need to note, supposing you contaminated this solution with litmus. You notice that when you add the litmus solution to the mixture of sodium chloride, the solution of sodium chloride, it's neutral. It's a neutral solution. But during electrolysis, the color of the litmus is different from both sides. What exactly have you seen? Can you discuss? Can you write down what has been observed at each of the electrons? Maybe probably pair the observation with the electron. Now, supposing I did this electrolysis as I have done, I use a U-tube and I put the zinc nitrate here. Solution, put the zinc nitrate in a U-tube, and this is zinc nitrate contaminated with litmus solution. I do the electrolysis, connect, right, so something like that. So we are aware that the electrons will move in that direction. So this will be the negative terminal. That will be the negative terminal, and that's a positive. So what's the reaction taking place here? So on this side, the ions that are moving towards that are the being positive, it will attract the nitrate ions and the hydroxide ion. Being negative, it will attract the hydrogen ions and the zinc 2 plus ion. So the ion being discharged here will be the OH ions. Now, removal of OH ions has the effect of decreasing the pH. Now let's look at it this way. If I have a solution here, that is water at pH 7, then I add sodium hydroxide. Add sodium hydroxide. What will happen to the pH? The pH will increase, becomes more basic, towards 14. Why? Because I've added the hydroxide ion. Therefore, the addition of hydroxide ions raises pH. Removal should have the reverse effect. Removal of OH ions lowers the pH. Similarly, the removal of hydrogen ions raises the pH. Why? If I have a solution here that is water at pH 7, I add hydrochloric acid. What about is hydrogen ions? What happens to pH? It decreases towards 1. So, addition of hydrochloric acid, addition of hydrogen ions lowers pH. Therefore, removal of hydrogen ions should raise the pH. So, in this side, the pH is raised. Why is it raised? Because I'm removing hydrogen ions. So what is the kind of litmus in a basic solution? So this side I will see a blue color. Now this side it will change to red color, and there shall be a border around there. But if you mix the two solutions, then it will just be neutral, because there is an increase followed by a decrease. The overall effect is actually nil. We are saying if the solution is contaminated with litmus or any other indicator methodology, you'll be able to see the pH on both sides. Removal of hydrogen raises the pH. Addition of hydrogen, addition or removal of OH will lower the pH, but raise and lower, the overall effect will be 0. Now another example, the electrolysis of dilute copper sulfate, this time using graphite electrodes. Maybe before you continue to look at the way I've tackled that particular electrolyte, why don't you take a moment and complete the table for the electrolyte at heart. What is the electrolyte that we are handling? And what electrode are we using? What are the ions present? Just record the cations and the anions. And which of the cation is discharged at the cathode, and why? Write the equation. And what about the anode? What is discharged? And what is the reason? At the back of your mind, just get to know why is it that substance is being discharged. What do you see at the cathode, and what do you see at the anode? Are there some other characteristics of the electrolyte that will be affected? Like, what will happen to the pH, the solution? What about the color and the concentration? What will happen to each of those characteristics? Then you can also look at what I've come up with for the same electrolyte. the ions present, copper ions and sulfate ions from copper sulfate, hydrogen ions and hydroxide ions from water. Now we should be familiar with that. We should be familiar with that. Now, at the cathode, what is competing for discharge? The copper and the hydrogen ion. What will gain preference? We are talking about the opposite electrochemical series. Hydrogen is only above copper, silver, mercury, and gold. So between copper and hydrogen, copper gains preference. It is less reactive than hydrogen. So copper gains preference. To get copper metal, so if you are using graphite electrode, the graphite electrode will be coated with a brown metal. Brown coat. Brown coat will be formed on the graphite electrode. The other side, OH is competing with the sulfate ion for discharge. What gains preference? The OH ion gains preference. It is lowest actually. That's what you've already said. And the equation is a familiar equation. So the observation is bubbles on that particular electrode. Now what happens to the pH of this solution? No effect on this side. What is the effect on this side? The removal of OH ions. If addition raises, removal lowers. So there is a decrease in pH. This reaction leads to a decrease in pH. So if the pH decreases and it is not affected here, the overall effect is a decrease. In fact, you can see that you have removed copper and you have also removed hydroxide. What have you remained with? Sulfuric acid. So the pH should decrease. Now these are the ions responsible for the blue color of this solution. The copper ions. The copper ions are responsible for the blue color of that solution, but you are removing them. What is the effect therefore on the electrolyte? The color of the electrolyte will fade. It will fade. The color will fade. Why will it fade? Because we are removing the ions responsible for the color. The second factor that affects the discharge of ions is the concentration. Allow me to say at the onset that the other factors I will talk about may not affect the cathode process, apart from some very few cases that I will specify. So this one, the concentration will affect the anode process. Now let's look at it this way. If the solution is, say, dilute sodium chloride, we have very few of the chloride ions. The OH ion will gain preference. But when it is concentrated, what will happen is there will be very many chloride ions, that will block the hydroxide from getting to the anode. But when you get to the cathode and the sodium ion is competing with hydrogen ions, irrespective of how many sodium ions you have, even if they are very many, the hydrogen ion is a very small ion, so it will still penetrate and be discharged. So the hydrogen ions may not be affected by concentration because of its small size, but the OH ion is big. The halides, the ions from the halogens, because that is mostly what is affected by the concentration. They are also big. When they line up around the electrode, they will prevent the OH from accessing that anode. So the chloride ion will gain preference over the OH. So what am I saying? The concentration does not affect the cathode process because the hydrogen will always penetrate. But the anode process can be affected, but only if the halogen is competing with the halide ions are competing with the hydroxide. So if the chloride is competing with the hydroxide, the two are very close in the electrochemical series. So the hydroxide or the chloride will gain preference. But if it is a nitrate, if it is a sulfate, if it is a carbonate, they will never be affected by the concentration. So if you have a dilute solution of sodium nitrate, and those are the ions present, H and OH, if it's dilute, you will get the OH. If If it is concentrated, you still get the OH. The concentrate does not affect the nitrogen, does not affect the carbon, does not affect, it only affects the halogens. And now we will remove the fluoride ions from there because the fluoride will never be affected by concentrate. It is a question of how close are they in the electrochemical series. If they are close, like happens here, then it can be affected. Because when you are doing the electrochemical cells, we discovered that if the potential depends on concentration. That's why when you are measuring the standard electrode potentials, we start to 1 molar solution, because an increase in concentration will lower the E value. It will lower the E value. So so the concentrate affects whatever is going to be discharged, but only if the two elements are very close to each other, as happens with the halogens, the halides. Here is an example. We are looking at the electrolysis of sodium chloride. In the first case, we are looking at the dilute sodium chloride, and we are still using graphite electrode. What are the ions present? Maybe before you continue to look at the way I've tackled that particular electrolyte, why don't you take a moment and complete the table for the electrolyte at hand. What is the electrolyte that we are handling, and what electrode are we using? What are the ions present? Just record the cations and the anions. And which of the cation is discharged at the cathode, and why? Write the equation. And what about the anode? What is discharged and what is the reason? At the back of your mind, just get to know why is it that substance is being discharged. What do you see at the cathode, and what do you see at the anode? Are there some other characteristics of the electrolyte that will be affected? Like, what will happen to the pH, the solution? What about the color and the concentration too? What will happen to each of those characteristics? Then you can also look at what I've come up with for the same electrolyte. The sodium ions and the hydrogen ions. Sodium chloride from the salt, hydrogen and OH from the water. Always remember that. At the cathode, sodium is competing with hydrogen, electrochemical series, hydrogen gains preference. The OH is lowest, it will be discharged. So the observations, as we've said in the past, the volumes, the volume ratios, the result, the effect on the concentration, we are removing water. So let's look at the electrolysis of brine. We are still using graphite. Maybe before you continue to look at the way I've tackled that particular electrolyte, why don't you take a moment and complete the table for the electrolyte at hand. What is the electrolyte that we are handling, and what electrode are we using? What are the ions present? Just record the cations and the anions. And which of the cation is discharged at the cathode and why? Write the equation. And what about the anode? What is discharged? And what is the reason? At the back of your mind, just get to know why is it that substance is being discharged. And what do you see at the cathode? And what do you see at the anode? Are there some other characteristics of the electrolyte that will be affected? Like, what will happen to the pH, the solution? What about the color and the concentration too? What will happen to each of those characteristics? Then you can also look at what I've come up with for the same electrolyte. Electrodes. So what are the ions present in brine? This brine is a concentrated sodium chloride solution. Remember, concentrated is not the same as molten. So it still has water, only that's a little amount of water. So the cations are sodium ions and the hydrogen ions. We still have water, so we have hydrogen ions. The anions are the hydroxide ions and the chloride ions. We still have water in that. Now, what is the rate that takes place at the cathode? Hydrogen competing with sodium for discharge. Doesn't matter how concentrated it is. As long as it's not molten, the hydrogen still gains preference. They are very small, cannot be blocked. We get hydrogen. Hydrogen gas and aqueous and hydrogen gas. Then at the anode, the OH is competing for discharge with the chloride ion in a concentrated solution. What gains preference? Right, the chloride ion gains preference because the competition between the OH and the halide is affected by concentration. So we have the chloride ions. So what does it form? Chlorine plus 2 electrons and aqueous. That's so you get bubbles of a green gas. The chlorine should be green. That's why we get the name chlorophyll. The green coloring matter. The green color of bubbles of a green gas that breaches a litmus paper. Then you get bubbles of a colorless gas that burns in a pop sound when impure. So I hope you will realize that the resultant solution is going to be basic. We're going to end up with a basic solution because you have removed hydrogen, you have only removed chloride. So removal of hydrogen leads to an increase in pH. You are having more of the hydroxide ion. So a basic solution will be produced from that. Finally, the factors that affect the discharge of ions, the nature of electrode. Now for this discussion, we shall classify electrodes into two. We have active electrodes and inert electrode. Note, an electrode does not become active if it reacts with the product. Hey, that's interesting. You will come across an electrode is like when you manufacture sodium metal. When you extract sodium from the trace of molten sodium chloride, you are told you cannot use steel anode. Why? Because the anode you react with with chlorine. Iron, you react with chlorine to form iron. That does not make iron an active electrode. Because it does not interfere with what is produced there. It is only reacting with what is being produced. It's not that because you have used iron, you are getting a different product. You're not going to get oxygen because you're using iron. The same will apply to the electrolysis of the extraction of aluminium using graphite anode. And we are told that you have to keep replacing the graphite anode. Why? Because it will react with the carbon, with the oxygen that is being produced there. But that does not make the graphite an active electrode, because you are still, whether you use graphite, you are getting oxygen. You're not getting a different product because you used graphite. It is not interfering with what is being produced there. So an active electrode is one that interferes. So there is competition between hydrogen and OH. You use this electrode, you get hydrogen. You use this electrode, you get OH. So depending on the electrode you have used, you're getting a different product. That is an active electrode. That's an active electrode. An inert electrode, the only thing it does is carry electrons. It's carry electrons. So examples of inert electrode are graphite and platinum. It's very difficult to ionize graphite. It is impossible that you get carbon 4 plus ions. Or platinum is one of what we call a coinage metal. Very inert in nature. It only carries electrons. It cannot really ionize. Now let's use an example to illustrate this. And we are thinking of the electrons of copper sulfate using copper electrodes. Now copper and hydrogen are the ions present at the cations present. So the reaction will be as expected. Copper and hydrogen, copper is below. So copper will gain preference to get copper in the solid state. Now when you get to the anode, now there are three things that can happen here. OH can lose electrons to form water. The sulfate can lose electrons. Of course, this is unlikely. You have never seen it happen. So this one, if we are comparing all these to this, we'll get. But then there is something else. The copper electrode itself, it is capable of losing electrons to form copper 2 plus. The copper electrode can lose electrons. The rod itself, it is now interfering with what is being discharged there. It is an active electrode. And this is a reaction that requires the least amount of energy. That's our reaction. So the copper rod will ionize to form the copper ions. So it is the electrode that is ionizing. A similar process can take place if I use silver electrode in silver nitrate. So the silver metal will ionize to form silver ions. It's the one that most readily loses electrons, more readily than the OH, more readily than the sulfate, more readily than the nitrate. It can readily ionize to form the. So what are the observations made here? Now this copper will be deposited on the rod, so there will be an increase in the size of that electrode. The electrode is ionizing to form copper ions, so there will be a decrease in size of this. This electrode will wear out, it will decrease in size. As this one increases in size, what happens in the color of the solution? We are removing ions and introducing ions. Overall change, nil. We know change in the color of that solution because you are replenishing the ions that you have removed. These are the factors that affect electrolysis, that affect the discharge of ions, the concentration. So what do you need to remember? The person in the electrochemical series, you need to just remember H competes with others. So H will always gain preference, apart from if it is copper, silver, mercury, and gold. You need to remember that for OH, it is the lowest. Then you go to the concentration. That only affects the cathode process, and the anode process, and only if the OH is competing with the halogens, not anything else. Concentration. Now the nature of electrode. We have active and inert electrode. An active electrode may be a metal in a solution of its own ions. It is likely to, the anode is likely to ionize. We shall give other examples where we shall affect the cathode process. Now the next thing that we shall look at is the application of electrolysis. The application of electrolysis. We have a number of ways in which electrolysis is useful in the industry. One of them is the extraction of reactive metals. Metals from potassium all the way to aluminium must be extracted by electrolysis. Now what we are saying is, and this is a topic that we shall tackle in details, metals, the way we find them are not, that's not the way they are found in nature. Very few metals will be found native. Okay, we may have some bit of copper, mercury, some of them may be found in a combined form, but most of the metals will be found in combined form, in form of compounds. The compounds could be sulfides, it could be chlorides, but at the end of the day, whatever metal you are talking about will be found in form of a compound. It will be found in form of a compound, combined with something else in form of ions. So you must supply some electrons to that, and electrons shall be supplied to that to form the metal. In a process that of course is a reduction process. The source of those electrons, as we shall soon discover, will depend on how reactive that metal is. So for some metals, you may just need to heat. The case of mercury, if it's found in form of the sulfide, you heat mercury sulfide, you may get the oxide, but the oxide is too unstable. It will just decompose to form mercury. Now some other substances, you can obtain those electrons by chemical reducing agent. We talked about competition for combined oxygen in form 1. So that if you heat iron 2 or iron 3 oxide with carbon, it will remove the oxygen from iron, and you'll end up with iron. You'll end up with iron from the iron 3 or iron 2 oxide. You have reduced. You have separated the electrons, but the electrons have now come from a reducing agent. Sometimes you can use hydrogen, and we shall talk about that in details. But for these metals that are very reactive, we don't have a suitable chemical reducing agent. No, nothing will actually remove those electrons. So you must use an electric current. So to extract potassium, sodium, magnesium, calcium, all the way to aluminium from their compounds, from their ores, you must use an electric current. The other application is a purification of metals. So once the metals are obtained, once you have extracted metals like copper, we will still talk about zinc, then you can refine it. So whatever you get is not going to be very pure. It will contain some impurities. Now, to refine now means to purify. You refine it. You get a purer form of the ore. Like in the case of copper, you obtain it you obtain blister copper. Then you do the electrolysis of blister copper, in which case you shall use a copper sulfate electrolyte. Then you'll have a pure and impure, the so-called blister copper. Now the blister copper should form the anode so that it ionizes. So it ionizes, so you'll get the copper 2 plus, the equation. The cathode is a type of reaction that you want. So once these are formed, they will be deposited on the cathode. So inside the pure mole of that is going. Then at the anode, the reaction at the anode looks like that. So where this anode will disintegrate, it will break down. So the ions will be deposited on that pure copper. So this one will reduce in size, you'll be breaking it down, and then there'll be a sludge. A sludge will be deposited there. The sludge should contain silver, gold. So that will be deposited there. So you'll be able to transfer the copper from here to the other side, sort of transferring it. So that you get the buildup of the pure copper, but this one decreases. So that's an application of the electrolysis of copper sulfate using copper electrode. Is electroplating. What is electroplating? Of course, it just refers to coating one metal with the other, but by means of an electric current. Yes, because you can use a brush. Like I think in galvanizing, we don't use an electric current. All you need to do is get the iron sheet, immerse it into molten zinc. You have not electroplated. Yes, you have coated the iron with zinc, but that's not electroplating. So you must use an electric current when you are electroplating. And why do we electroplate? We electroplate for two reasons: to improve on the appearance. You get an iron or a steel ring. You just coat it with silver. It looks better. Now then, you can also electroplate in order to prevent corrosion, because in most cases you'll be coating it with a metal that is raw in the reactivity series. So what shall you need for electroplating? Okay, now the iron ring that you want to electroplate may be made from from wires cut from a fence. Okay, that's interesting. Then maybe you can insulate this part. Now you want to gold plate or silver plate? Fine, let's silver plate. So you can use a silver nitrate electrolyte in aqueous state. Now the whatever that is supposed to be electroplated should form the cathode. Because what do I want? I want the silver plus an electron to form silver. This silver will be deposited on that ring. Now this one should be made from silver. This one is a silver electrode, and this is silver nitrate. So, but you need to ensure that the electrolyte is very dilute. Very dilute electrolyte, and the current flowing should be very low. The voltage that you're going to use, so that you can electroplate slowly. The slower the process, the firmer the coat that you're going to deposit on that. In fact, some people say that you should make whatever that is going to be electroplated as rough as possible. It should be very rough, so that whatever you are coating it with will stick properly. So dilute solution, a low current, a rough surface, and ensure that this is whatever you want to coat is what makes up the electrolyte and that particular electron. So when that reaction takes place there, the silver will be deposited. Then of course the other side will have the silver replenishing the ions, replenishing the ions that you are coating on the other side. So that is if you want to silver plate. If you want to gold plate, of course use a gold, an electrolyte that is made from gold. I've heard of gold cyanide on whatever layers, as long as it's made from gold, and the electrode is also made from gold. That's another application of electrolysis. I hear of another application that is called anodizing aluminium. That is your homework. Try to find out what anodizing aluminium is all about. Now allow me to say something about this other process. Yeah, the manufacture of sodium hydroxide, hydrogen, and chlorine. Now all these will be manufactured from the electrolysis of brine. Remember, brine is a concentrated sodium chloride solution. So what does it contain? Sodium ions, chloride ions, hydrogen ions, and hydroxide ion. I hope we have not forgotten these ions that comes from water. Now, during electrolysis, the hydrogen ions will be discharged. Yeah, let's say hydrogen ions are discharged at the cathode, and now that's a concentrated solution. Let's get the chloride ions at the anode. So you have managed to get hydrogen, you have managed to get chlorine, and now whatever remains will be sodium hydroxide. So that is simply what you need to do. Just carry out the electrolysis of brine, remove hydrogen, remove chlorine, but you remain with sodium hydroxide. But then a problem arises. What problem is this? Sodium hydroxide, so formed, can react with chlorine to produce what? Whatever is produced will depend on the concentration. So you can get to sodium hypochlorite, of course sodium chloride and water, and an equation that is not very difficult to balance. I think it's already balanced. Apparently not really. Sodium 1, oxygen 2. Let me put a 2 there. There are two sodium and 2 sodium, 2 oxygen and 2 oxygen. That is 2 hydrogen, and 2 chlorine. Yeah, the equation is already balanced. So this is when it is cold and dilute. The result of that will be the reduction in the amount of chlorine and you need the chlorine, but this reaction leads to a decrease in the yield of chlorine. When you continue, and then maybe you get the hot concentrated sodium hydroxide, it will react with chlorine to form sodium chlorate plus sodium chloride plus water. Again, we can try balancing the equation once the equation will be balanced. So when it is hot and concentrated, I will get the sodium chloride. Again, that has the effect of reducing the yield of chlorine. So something must be done in order to ensure that the chlorine does not come into contact with sodium hydroxide. And what is that needs to be done? We use a special cell. And there are two types of cells that can be used for this purpose. And the first type of a cell is a flowing mercury cathode cell. As the name suggests, the cell consists of a flowing mercury cathode. So this is mercury, and it is flowing. It is flowing. So that is connected to the negative terminal. So it becomes the cathode. And mercury is a metal, so it will conduct an electric current. Then you also have the anode that is made from graphite. We need something that is not going to react with the chlorine. So we introduce brine through this that opening, the opening there. Introduce the brine, and the anode chlorine will be produced. So around here chlorine will be produced. What is the reaction for the production of chlorine? Chloride to form chlorine plus 2 electrons. So that reaction takes place on all these electrodes, and then the chlorine is going to be corrected. Then the spent brine, of course, can leave. Now, of course, on this electrode now, the flowing mercury, a reaction is taking place. As the mercury flows, as the brine flows also, a reaction is taking place here. Now, the hydrogen is competing with sodium for discharge. Something interesting happens. So when hydrogen competes with the mercury for discharge, and the electrode is made from mercury, sodium gains preference. Interesting. The nature of the electrode. We normally say that hydrogen has a high mercury over potential. Now, this is the way I look at it. Supposing on this electrode you produced hydrogen. So the hydrogen produced will dissolve in mercury. But hydrogen is an non-conductor. It will not conduct. It's found in form of molecules, so it will not conduct. So what you will do is to increase the resistance of the mercury. You increase the resistance of the mercury because you have dissolved in it something that does not dissolve. So the voltage that is going to be required to continue producing mercury is going to be very high. So we say, so you have a high over potential because the mercury that the hydrogen that dissolves in the mercury makes it a non-conductor. It reduces the conductivity. But look at what will happen when you produce sodium. So sodium plus an electron to form sodium. Sodium dissolves in mercury, and what you get? A sodium amalgam. A sodium amalgam will be obtained. But sodium is a metal, so it will continue to conduct an electric current. It does not therefore increase the resistance of the mercury. So when the hydrogen competes with mercury for discharge, and the electrode is made from when sodium competes with hydrogen for discharge on a mercury electrode, sodium gains preference because the over potential, the hydrogen over potential is quite high. So the mercury will produce sodium, and the sodium will dissolve in it, and then which continues to flow. As you correct the spent brine, then the mercury will continue to flow. Then you can introduce water from this end, so it will be forced upward as the mercury flows downward. The interaction between the mercury and the sodium, the multi-amalgam and the water, will of course produce sodium hydroxide plus hydrogen. So the hydrogen can be corrected, and then the mercury will be regenerated. You regenerate the mercury. Mercury now flows and can be pumped up, and the process continues. It is being recycled. So you know that you're producing chlorine on a different compartment, you are producing sodium hydroxide on a different compartment. They don't come into contact, therefore they don't react, and that is what we call the free mercury cathode cell. Now this process has one major advantage, that whatever sodium hydroxide you will get is going to be very pure. The only thing that it may contain is a bit of water, maybe 50% water, but that can easily be removed by evaporation. So it's very pure. However, the process is expensive. Mercury is an expensive substance and also poisonous. If you want to know how poisonous it is, ask the people of Minamata in Japan. Minamata, visit Japan one day, ask them what happened in an area that is called Minamata. And if they don't give you the details, just get to the Kumamoto University and ask them of the research that they did on the poisoning in Minamata, where the fish were found to have a very high concentration of mercury. So the result were cats were almost getting paralyzed. Then immediately after a few days they go into a coma, and then they eventually die. The same condition killed quite a number of people, but that was due to the industry that had been set up to manufacture PVC. They were using the free mercury cathode cell to produce chlorine for the manufacture of PVC, but their discharge system were not good. They were discharging into the ocean. Then the fish get the mercury. The mercury get into the people, but through the cat first. Although I think the cat was rest resistant, so the cats were the first victims. But people died out of it because of poor waste disposal. Another cell that can be used to produce chlorine is what is referred to as a diaphragm cell. As the name suggests, there is going to be the use of a diaphragm, probably made from asbestos. So you just want compartments so that the sodium hydroxide and the chlorine are not produced in the same compartment. Now in this cell, therefore, you will have the anode, so you will produce the chlorine first at the anode. So you still have brine consisting of the same hydrogen and the hydroxide ion, but you start by producing the chlorine. So remember we said that production of chlorine does not interfere with the pH. So whatever that will be flowing in this direction will still be neutral. It will still be neutral. It contains water and a bit of sodium ions dissolved in it. So it will not have interfered with the pH. And note, when you remove the chlorine by the usual reaction, then the level is higher on this side than the other side. Why is that so? So that there will be flow in that particular direction. The electrolyte flows in that direction and not in the reverse direction. So when you get to the cathode now, you can remove the hydrogen. You can now remove the hydrogen because you are using a graphite electrode, and that leaves you the sodium hydroxide that can be tapped. But it will contain a lot of sodium chloride impurities. That is the disadvantage of that process. The sodium hydroxide will contain a lot of sodium chloride impurities. You can separate it by fractional crystallization, as we learned in acid, bases, and salt. And that is briefly how you can get the sodium hydroxide, the hydrogen, and the chlorine. What are some of the uses of the three substances? Sodium hydroxide, I could talk about manufacture of soaps and detergents. I could talk about the extraction of aluminium in that is the purification of the ore. I could talk about the fractional distillation of air to remove carbon dioxide, and you can come up with others. What about hydrogen? We learned a few uses of hydrogen in Form 1. the oxyhydrogen frame for welding, the hardening of oils. Hydrogen can also be used in manufacture of ammonia and hydrochloric acid. Those are some uses. But what about the use of chlorine, PVC, water treatment, making breaches, and you can think of others. So let us wind up this topic by looking at the quantities of substance that are produced or discharged during electrolysis. In this particular session, we are interested in the question of how much. Now we have said that during the electrolysis of copper sulfate, maybe we are using graphite electrode, we shall get some copper deposited at the cathode. Some copper will be deposited at the cathode. We will get some oxygen at the anode. So the question that we want to answer now is, how much copper will I get? How much copper will I get during this process? The quantity of copper. So we start by asking ourselves one question: what will determine the amount of substance that will be discharged during electrolysis? What will determine the amount of copper that I have? Now, supposing I use one cell, one battery, as it were, then I carry out the electrolysis for 20 minutes. Then somebody repeated the experiment using one cell, but he does the experiment for 30 minutes. Obviously, the person who's doing it for a longer time will get more copper. So one of the factors that will determine the amount of substance discharged during electrolysis is the length of time. That's a rather obvious one. The more time you have, the more substance that you'll get. But what about if I now don't use one cell, but I use two of them or even three of them, use three of them in parallel, in series, and then I pass the current for, say, 20 minutes. I started with 20 minutes. Now I have three of them, 20 minutes. I'll obviously get more substance if I did it for a long time. So the two factors that affect how much substance I'll get during electrolysis are the time and the quantity of electricity passed. But the physics people will tell us, and that is elementary physics, they will tell us that we can combine time and the current passed into one thing that you call the quantity of charge passed, measured in coulombs. So a coulomb is a current of 1 ampere passing for 1 second. That is a coulomb. A coulomb. 1 ampere passed for 1 second. So it goes without saying, therefore, that if I pass 2 amperes for 1 second, then how many coulombs do I have? I have 2 coulombs. So because an ampere for 1 second is 1 coulomb. So if I have 2 coulombs, if I have 2 amperes for 1 second, then I have 2 coulombs. So supposing I have 2 amperes for 5 seconds. How many coulombs do I have? If I have 2 amperes for 5 seconds, 1 ampere for 1 second is 1 coulomb. So 2 amperes for 1 second is 2 amperes. But 2 amperes for 5 seconds will therefore be 2 times 5, which is equal to 10 coulombs. So actually, to get the quantity of electricity passed, all I need to do is to multiply the amperes with the, I multiply the current in amperes with the time, but the time must be in seconds. The time must be in seconds. So whatever I'll get is a quantity of electricity Q in what we refer to as in coulombs, in coulombs. So is amperes times the time in seconds. So that is the definition. The quantity of electricity is measured in coulombs. The quantity of electricity passed from 1 ampere is passed for 1 second. So let's find out. Supposing a current of 3 amps is passed for 1 hour. What is the quantity of electricity or quantity of charge that has been passed? Right. So Q is given by IT. So I is 3 amps times time. Time, 1 hour. 1 hour is 60 minutes. But 60 minutes is, so I multiply, so because I have to convert that in seconds, because this amps, the amps times the seconds, so that is equal to what, that 360, 980, 9800, that is coulombs per, no, this is amps per second. Amps per second, but amps per second is equal to coulombs. So 98, and we can confirm that. You can confirm that that is 36 times 3. 108 coulombs. That is amps per second. I mean, so the only thing you need to remember is to always convert the time to seconds, because the amps per second is what is a coulomb. The amps per second is what is equivalent to a coulomb. Otherwise, if the time is in minutes, then that is not, you cannot equate that to a coulomb. Relationship between the quantity of electricity passed and the amount of substance that is discharged. You increase one, you also increase the other. You increase the quantity of electricity passed, you also increase the amount of substance that is discharged. So they are directly proportional. So that relationship is what is referred to as the Faraday's first law of electrolysis. So the Faraday's first law of electrolysis states the amount of substance discharged during electrolysis is directly proportional to the quantity of electricity passed. You increase one, the other one increases. So that's obvious. The more the quantity of electricity passed, the more the substance that you are going to get during electrolysis. Now, let's simplify this further. So let's think about the electrolysis of, say, sodium chloride, molten sodium chloride. Now I will get some electrodes. The cathode is what I'm interested in. Now, an electron will move from there. An electron gets here. An electron is picked by sodium. So I'll get a sodium plus, add an electron. Now this one electron has a charge. That one electron has a charge equivalent to 1.6 something 01 times 10 raised power minus 19 coulombs, or amps per second. So that's the charge of one electron. But if I want 1 mole of sodium, I will need 1 mole of electron. So if I discharge 1 ion of sodium, I will need 1 electron that has that charge. If I discharge 1 mole of sodium, I need 1 mole of electrons. But 1 mole of electron is 6.023 times 10 raised power 23. Those are the number of moles of electrons that I need, but I have Each of the electron has that charge. So for 1 mole of sodium, I need all this quantity of electricity. Now when you work out that, it will come to 96,487 coulomb. That is rounded off to 96,500 coulombs. Now this is called the Faraday's constant. I hear some people calling it a farad. Now let me call it a Faraday's constant. What is a Faraday's constant? And now this is important. You grasp this, you are through with the quantitative aspect of electrolysis. What is the significance of this? It is the charge on 1 mole of electrons. It is the charge on 1 mole of electron. It is not the charge of 1 mole of sodium. It's not the charge of 1 mole of hydrogen. It's not the charge. It is a charge on 1 mole of electron. Right. So, if you are discharging sodium, you need 1 mole of electron. That means you need 1 Faraday. You need 1 Faraday for 1 mole of sodium. But if you are discharging 1 mole of calcium, in which case you need 2 moles of electrons. How many Faradays shall you need for that? Now that you need 2 moles of electron, and the charge on 1 mole of electron is that, so you need 2 Faradays because you need 2 moles of electrons. And you can do it if you have an element that has a charge N+. Then to get 1 mole of M, you need N Faradays, or N times 96,500 coulombs, because each electron will have that, each mole of electron will have that charge. Now it becomes a bit interesting for gases, because for hydrogen, what you have hydrogen like that, but you got to get a molecule of hydrogen. So for every molecule of hydrogen, you need 2 moles of electrons. What is that equivalent to? That is 2 Faradays. That's 2 Faradays. So the number of moles of electrons that you need, now multiply by the, each mole of electron will be 1 Faraday and 6,500 coulombs. So when you grasp that this is a charge on 1 mole of electron, then you can attempt any question. For instance, on the first example, the mass of copper deposited at the cathode on a current of 2 amperes is passed through copper 2 sulfate for 32 minutes. Now let's first ask ourselves, how much electricity is that? How much electricity has been passed? That is Q is equal to IT. I is 2 amps times T, 32 minutes, but the time must be in seconds, so times 60. That is equivalent to 840 coulombs. That's the quantity of electricity that have passed. Now, but the equation for the discharge of copper is copper 2 plus 2 electrons to form copper. I don't need the states, but I can write aqueous and sorry there. So I need 2 moles of electrons. For every mole of copper, I need 2 moles of electrons. That is 2 times 96,500 coulombs will produce 1 mole of copper, which is 63.5 grams. So now that I have that 3,840, how many grams will I get? Simple cross multiplying times 3840 divided by 2 times 96,500. And that gives me 1.263 grams to 4 significant figures. That is what I get. Of course, the alternative would be maybe convert these to the moles of electrons. So if I have 1 mole of electron, 1 mole of electron has a charge of 96,500 coulombs. 3840 is how many moles of electrons? I can do that. 0.03979 moles. But moles of what? Those are not moles of copper. Those are moles of electrons. Those are moles of electrons. But for 1 mole of copper, I need 2 moles of electrons. For 1 mole of copper, I need 2 moles of electrons. Now, I have 0.03979 moles of electrons. How many moles of copper will I get? I need to divide that by 2. And then, whatever answer I have, convert it to mass, using the relative atomic mass of copper. So, either way, only remember, these are moles of electrons and not moles of copper. Moles of electrons, not moles of copper. Because this is a charge on 1 mole of electron. 1 mole of electron. Unlike here when I said this is the amount of electricity that is required for 1 mole of copper. Because I multiply, I need 2 moles of electrons. That is what I get. So the first thing is I calculate the quantity of electricity first. Q is equal to IT 1000. This has to be converted to seconds. Remember that? So that is the amount of electricity I get. Then I wrote the equation to get the amount of electricity that is required per mole of aluminium. So note I need 3 moles of electrons, but each mole of electron is 96,500 coulombs. So if you got it wrong, I think you equated that to that. I can bet. You equated that to that. You did not remember that you need 2 moles of electrons for that. And that's cost you everything. So times that, then I got 1,678 grams to 4 significant figures. Now calculate the volume of oxygen produced at the anode when a current of 4 amperes was passed through dilute hydrochloric acid for 18 minutes. It's dilute, so it's going to produce oxygen. Of course, with time it may produce some chlorine. So the molar gas volume at RTP, so we are working at RTP. So what do we do here? 4 passed through for 18 minutes, so Q is equal to IT, my starting point. Q is 4 times 18 times 60. Conversion to so 4 Faradays will be needed for 1 mole of oxygen. Here's my answer. Compare with yours. So when a current of 1.5 amperes was passed through a cell containing ions with a charge of a metal M for 15 minutes, the mass of the cathode increased by 0.26. 1 Faraday is that determine the relative atomic mass of M. Okay, where do we start from? Let's just get the quantity of electricity passed first. 1.5 times 15. Eh? Where do we get to? This is what is produced 0.26 grams. I want to find out what will produce 1 mole. Because, or I can convert it to Faradays. I want to find out, oh sorry, I have 3 Faradays here for 1 mole. I want to find out the mass that will be produced by 3 Faradays. Because 1 mole will require those number of Faradays. 1 mole requires 3 Faradays. So I can convert to Faradays, but can still work with Coulombs. 1350 produces 0.26 grams. What about 3 Faradays? Because M 3 plus 3 electrons to form M. For every mole of M, I need 3 Faradays. So 3 times 96,500 coulombs will produce how much? That will be the mass of a mole. That will be the mass of a mole. Don't put units, because relative atomic mass does not have units. The moment you put G there, you lose half a mark. So let's get the quantity of electricity first. That is 0.5 multiplied by 32 multiplied by 60. We need to add 10 to that. What does that give us? It comes to around 965 coulombs, not around exactly that. Now, I don't have an equation because I don't have the charge on Q. But I can work out the number of moles that are produced by this quantity of electricity. 1 mole is 88, 0.44 grams is how many moles? But I can do the kienyeji style. Kienyeji is Greek, those of us who don't speak Greek. So this one will be produced by 0.44 grams, so 88 grams will require how many coulombs? That comes to 193,000 coulombs. So for 1 mole of P, I need those number of coulombs. That is, of course, equivalent to 2 farads. So 1 mole of Q, P requires 2 farads. What does that mean about its charge? Of course, it is a divariant. It's divariant. Assuming it's positive, it is a divariant substance. So it's 2 positive. An example that you can write down and attempt. Some lead 2 bromide is heated in a crucible. Why are we heating to melting? So that you can have mobile ions. Then you insert 2 graphite electrodes to the crucible. A current of 1.8 amps passed for 12 minutes. You want to work out the mass of lead deposited. Lead is 207. Relative atomic mass of lead is 207. Find out the mass of lead that will be deposited. See if you get 1.39. What about the volume of bromine produced at altitude? Compare your answer with your deskmate or a neighbor, a friend, and see what. Agree. If his answer or her answer does not look like yours, hers is wrong. So convince her that yours is the correct answer, and vice versa, and come up in the middle ground. So that brings us to the end of the topic electrochemistry, where we have looked at can a reaction produce a current. That was in electrochemical cells. Can a reaction produce current? Or can current produce reactions, the decomposition of substances? So if you can do the two, you can produce a reaction from a current, you can produce a current from a reaction, then we have achieved our objective in this particular topic. See you in the next topic.